In this video, we're going to discuss coordination of transition metal complexes in solution, in general, with some terms as to the material. What does it mean to coordinate to a transition metal? Well, transition metals don't tend to exist just as the metal ion in solution. Instead, what will happen is that they will bind various molecules to them. So some iron atom might have waters attached. You'll have an iron 2 plus, and it will just have waters that adhere to it. Various other things can also be attached at the same time. You might have, say, some chlorides, or maybe you have some ammonia. Now, at first, this looks like a Lewis structure, sort of. We have atoms bonded to other atoms, with the dash showing the 2 electrons. Well, this is really what's going on. That iron has orbitals. The various d orbitals, here's shown one of them. These can overlap with the lone pairs on our other atoms of these other molecules. Those lone pairs on oxygen in their sp3 orbital can overlap the iron d orbital. In doing so, there's 2 electrons occupying those orbitals, and so this orbital looks like it is filled with electrons from an outside source. Well, this has a favorability. Spreading electrons out over more space is favorable in general, and so by allowing those electrons to spread out over the d orbital as well, allows that negative charge to be spread out over a greater volume and reduces the energy of it. In general, we can get various molecules with lone pairs to bond to our transition metal ions. Since we often do this in aqueous solutions, water is a very common one. Other things may be a little bit more prone to doing so. Amine is a base. It's very good at loaning its electrons. Often they say pick up H+, but a Lewis acid and a Lewis base, if you remember the definition, a Lewis acid accepts electrons, and a Lewis base donates electrons. In this case, we are forming complexes. I have an ion, and multiple things are attaching to it, because that ion is acting as a Lewis acid accepting lone pairs, and the various molecules attaching to it is acting as a Lewis base donating lone pairs. And so in the same way ammonia can pick up an H+, ammonia can pick up an Fe2+. So what are some of these terms? Well, transition metals and molecules with the capacity to donate lone pairs can form complexes. Complexes are ions that are bound with ligands, which leads to the next term, ligand. Ligands are molecules or ions bonded to our transition metal. Complexes with their ligands have their own naming structure, which will be addressed later. The idea is we can have neutral molecules or anions attached to our cation transition metal. There are various ways that this can happen as well. So when our complexes bind our ligand molecules, they can take a variety of forms. For this, we also have some terms for the shape they end up taking. If you think back to your VSEPR theory, you might remember tetrahedral, you may remember linear, trigonal bipyramidal, and octahedral. As well as possible, you may remember square planar. These are geometries that our complexes can form around our transition metal ion. In our previous example, we had an iron center that went up and down, also went forward and back to the left and forward and back to the right. There were 6 ligands attached to our iron. 2 chlorides on top and bottom, 2 amines opposite, and 2 waters. Being 6 things around the center, this was octahedral. Depending on your metal, your oxidation state, and the availability of different types of ligands, various geometries can be taken. These would lead to various properties that emerge as a result, especially color of solutions and things like that. But these are the common geometries that we'd expect to find. Additionally, there's a variety of common ligands. Ammonia is often called amine when it's in a complex. Water is aqua. Carbon monoxide is carbonyl. NO is nitrosyl, as well as our halides. F-, Cl-, Br-, and I-. We can have neutral and anionic ligands. For anions, our fluorides, our chlorides, our bromides become fluoro or chloro. Basically, the ending becomes O instead of ide. All of these are under the auspices of monodentate ligands. Dentate, dental, bite. They attach once. This is because you can have molecules that have more than one nitrogen or oxygen that can attach to your metal. Ethylenediamine is a bidentate ligand. Having two different nitrogens on the molecule enables it to attach to the iron atom or any other transition metal twice. So you can also have bidentate and up to polydentate. A nice example of a polydentate would be the heme molecule. Think hemoglobin transporting dioxygen. Hemoglobin actually has an iron with several nitrogens connected, all on the same molecule. The heme itself is a tetradentate. It has 4 nitrogens that can bond to the iron. There's also amino acids that bond to a 5th site, and our dioxygen becomes the 6th site. So hemoglobin carrying dioxygen through your blood is an octahedral iron atom. 5 nitrogens arranged with an open site on top to capture the oxygen for transport. Complexes with transition metals don't just happen randomly in solution. They are vital for a great deal of biological function. They also experimented on a great deal to develop catalysts, at least homogeneous solution catalysts. Many industrial catalysts are heterogeneous, which do bind many atoms and transition metals in various ways. They're not as easy to study, and so exactly what their form and complex type structure might be isn't as well understood. And so in regards to some basic terms involved in complexes formed from transition metals, there are various molecules that can attach, there are various shapes it can take. When our transition metal binds several other things, we form a complex, and the things bound to it are ligands. We'll dive more into the geometries, how the ligands affect the behaviors of these complexes in further videos.